All right, we'll get started. So we have, today we'll just wrap up weighted least squares, and then we will introduce multiple linear regression. This is, I think, where things get more exciting. All right, so on Friday we talked about weighted least squares, and we fit it by using the optional argument weights in the LM function. Okay, and we calculated the weights. We had to mutate our data frame so that every single observation had a weight associated with it. Okay, and we talked about ways to calculate these weights, whether it's going to be, estimated variance or square root of the absolute value of the standard deviation, standard deviation or things like that. So we talked about calculating weights for each observation and then using LM to fit it. The only unfortunate thing with that is that you can't use the built-in functions predict or confidence interval based on those things because they assume constant variance, which is exactly not weighted least squares. Okay, so to do inference on a weighted least squares model, we have to transform our x and y variables. Okay, and so we are transforming our variables, but this is still weighted least squares. It's not the same family as power transformations, which we did with like the Box-Cox method and things like that. So those are power transforms. That's different. We are doing weighted least squares, but we're doing it by transforming our variables. Okay. So the weighted least squares transformation, basically, we are multiplying every single thing by the square root of our weights. Okay. So instead of y beta 0 beta 1 x plus error, we have square root w of y equals square root, all of this. You can see it right here. Okay, and so basically this we have our transformed y, our transformed x, x1 and x2. So notice that with regular least squares regression, the intercept is the same for every single observation. But because we are multiplying it by the square root of a weight, okay, and we have a weight for every single observation, this is now no longer constant for all the observations. And so we have to account for that by just saying now we have a new x here, okay? But essentially this x1 that says x1 new sub I, this is the notation the book uses. Just this transformed x is essentially just the square root of the weight. Is that okay? And then we have this, basically square root of w times x is our transformed this and all of this stuff. Okay? So this is the weighted least squares transformation. So to put this in R, we're going to start off with our data frame that where we left off last week, where we have, crews, our x variable, rooms, our y variable, and then we calculated the variance, which we're using for weights. Yes?
After the transformation, do we still assume that the EI is normal distributed 0, 1 as well?
No. So yes, this EI is no longer normal 0, 1. And that's because with weighted least squares, we no longer have the assumption of constant variance. So yes, this is, we don't have any assumption about this distribution. Okay, so that's why weighted least squares can handle situations of non-constant variance. Okay, so this is where we left off. We added the variance column. We created that lookup table. Remember the lookup table with the variances? We created that, and we used that to attach the variance column here. Okay, and so we're going to further mutate this And so I'm going to have weights, which is going to be 1 over variance, transformed y, which is going to be the square root of the weights times the original y, transformed x, which is just transformed x1, which is just the square root of the weights, transformed x2, which is square root of the weights times our original x variable. Okay, so all of these are here now. Transformed y, transformed x1, transformed x2. Okay, and so now we have weighted least squares with the transformed data. So we're going to create cleaning model, and this is a linear model, and we're taking transformed y as explained by transformed x1 plus transformed x2. Okay, and I put in a -1 here, and the -1 means don't do an intercept. Okay, so in linear model, it's not a literal -1 in the regression. It just means -1 means don't try to fit an intercept here, because if we go back to our model, the intercept is accounted for with transformed x1. Okay, and so here is the results of our weighted least squares model here. Okay, tx1, tx2, all of this. And so so just to compare this, this is what we had last time. We did rooms as explained by Cruz, and we did weights is equal to 1 over variance. Okay, and so if you look at all of these numbers here, the intercept and the Cruz are the coefficients for these are exactly the same. Notice we got 0.471 and over here, and then on the previous slide 0.471 -2. So we had in the same same t value, 0.725, same all of this. Okay, so transforming the data using the square root of the weights works as well. Okay, and so with that in mind, we can create prediction and confidence intervals. Okay, and so when you create a prediction interval here, it's going to create it like this, but then to untransform it, you have to multiply it by the square root of w. Okay, and so to untransform, you need to have an estimate, a knowledge of the weight that you should use. Okay, and so if we were to do something like create a prediction interval for 14 or something where we don't have data, then we couldn't do it. Okay, because we don't know what weight would have been used in that circumstance. I guess you can kind of try to infer it between values, but you can do it. So notice, so the prediction interval is kind of complicated to look up. Okay, so looking at this, the prediction interval, our model, to get a y, we require an x1 and an x2. Okay, so x1, if we go back, is the square root of the weight, and then x2 is the square root of the weight times our x variable. So to do this, our lookup table shows the variance, so multiplying it by the square root of the weight is the same thing as dividing by the square root of the variance here. Okay, so my x1 is going to be 1 over the square root of the variance for the number 4, and then the second one is going to be 4 over the square root of the variance for number 4. Okay, and so this is going to give me give me that. And then over here I've got transformed x1 is 1 over the square root for 16, and 16, because it's x over the square root of the weight, right? Or x times the square root of the weight, which is 1 over the square root of the variance for 16. Yeah?
Can you go back to the slide where you have -1? So can you explain again what it means to have no intercept? Because we're also estimating beta 0 and beta 1, right?
Yes. So let's look at the original model here, okay? So we have an intercept and we have a slope, okay? This is for the regular least squares model, and we can apply the weights here, or we can take this and multiply everything, both sides, basically by square root of the weight, okay? And so this now becomes this, all right? So we no longer have a constant that is independent of x, okay? We have a beta 0, but this is tied to the x. So we don't have, I don't have like another beta something over here or a gamma over here that's not attached to some kind of x variable, okay? So that's why for this thing, we say don't try to fit an intercept.
So is the x1 and x2 here the same thing?
Yeah, the x1 and the x2 here are the same thing as the intercept and the slope for the untransformed. Or I mean, yeah. Okay. So the estimates here, this is pretty much the intercept.
Right.
Okay. And this is pretty much the slope. It's just now we're dealing with a transformed variable. And we have and we can untransform it. And so to untransform it, we just have to multiply it by the weights, square root of the weights. Okay. And so you can create prediction intervals for weighted least squares this way, or any other method, and it's just a matter of, you know. So I like dplyr because it makes it very easy to create these additional columns, in my opinion. Okay. Any questions on that? Okay, so now we're going to introduce multiple linear regression, which I think is exciting. And so today I was just going to focus on the, I don't know, I guess just the math part. And I know so I'm skipping, well, I guess we can look at the derivations of some of this stuff, but it's all in matrix notation. Okay, so I'm going to just write out all of the things that I think you should know for multiple linear regression. Okay, so basically we're just going to expand linear regression to allow for more than one predictor. So rather than just having one x, you can now have p predictors, so p x variables. And polynomial regression is a form of multiple linear regression. Basically, the different predictors are just powers of x. And so we're going to use matrix notation. Okay. So this is how we would write out a multiple linear regression model. You've got the different x's. You've got x1, x2, x all the way up through xp. And each observation y, so y sub I, is made up of, you know, your constant beta 0, and then beta 1, x1, beta, you know, all of this, okay? So even if you think of like polynomial regression, it's still considered multiple linear regression because if you just define, the x squared as just another one of these x variables, everything is linearly related to each of the x variables. Okay, so you might have, x sub p is equal to x cubed, okay? But if you just say, here's just a new variable, and instead of calling it x cubed, you call it g, or y, or w, or x sub 3, whatever, all of the coefficients are just linearly related, okay? So y is just a linear relationship, or linear combination of these different x variables. Okay, and so in matrix form, we can just say all of the y's is equal to our x matrix multiplied by our beta matrix plus our epsilons, okay? And so actually, yeah, no, this is correct. So you've got y1 through yn. Okay, these are all y sub i's. And then you have an x which has n rows. So one row for every observation and one column for each predictor variable. So you have p columns. Maybe I should write that somewhere here. So n rows, one row for each observation. All right, that's actually p plus 1 columns for one for each predictor. Each predictor variable plus a intercept. Okay. And then you have the matrix of coefficients, which has p elements in it. Beta 0, beta 1, so your intercept, and then each predictor has its own coefficient, and then plus the error terms. Okay. Any questions here? So we all remember our linear algebra, all of this stuff. Okay, and so so the only difference between the actual and the fitted values is that, once we find our estimated parameter matrix, our estimated beta matrix, beta hat, then our fitted values are y hat is equal to x beta hat. So there's no error terms here. Okay. So this is all. So we, if you read the textbook, it shows all of the kind of derivations for this stuff, and I guess it's good to know, but I don't think it's necessary to know. But the things I put on the slide, I think are necessary to know. So these things you should know. Okay. The residual sum of squares, which is the thing that we're trying to minimize as a function of beta, or you can just think of residual sum of squares as this, and that the minimized one, you just put the beta hat in here. Okay. It's just basically, y minus whatever you're fitting here, transpose times. So you're basically just squaring the residuals, right? So if you think of what a residual is, being y minus kind of the fit value, you're essentially squaring it, but because it's a matrix thing, you got to do the thing transposed times the thing. So does this return a matrix, or does it return a single value? What does this return? It returns a single value, right? Because this becomes a row matrix, a row vector, and this is a column. And so you can go, or however you do it, you get a single value here. Okay, so that's why we can minimize it. Okay, and then so you take x transpose x inverse. You have to solve this, okay? And then x transpose y. This is how we get our estimated parameters beta hat, okay? And so the book has a whole page dedicated to how this is derived. And honestly forget how it's done. Every time, if you ask me how this is derived, I always have to look it up. But I do know that this was what it is. So I think it's kind of like if someone forced you to derive, what was that, the quadratic equation, you could probably do it, right? But I think at some point it's just easier to just remember what it is, although I've totally forgotten it. Negative b plus or minus the square root of 4ac over
b squared minus 4ac.
2a, yeah. Wait, b squared minus 4? It's whatever. Now I'm embarrassed that I've forgotten my 8th grade math. Okay, but anyway, so we have that. Okay, and then the residuals, just the standard, what you expect to be residuals, but in matrix form, so y minus y hat, or y minus x beta hat. Now we're gonna rip through all of these slides. Okay, so the variance of the model is assumed to be constant around the fitted values. Okay, so your variance of E is sigma squared times I. The I is the identity matrix with n. What is it? N dimension n. No, not dimension n. If you got n observations, you're going to have n rows and n columns with just ones down the diagonal. Okay, the identity matrix, size n, sigma squared. That's the variance. Okay, beta hat is an unbiased estimator of the true beta that exists in the population. That is to say, the expected value of beta hat is beta. Okay, and the variance of the estimated parameters beta hat is sigma squared times x transpose x inverse. Okay. And so you can kind of think of this as a multivariate generalization of sum of x squared. Okay. And so if you compare, I probably should have, if we compare, let me pull up the results for simple linear regression to multiple linear regression. I think you'll see a lot of similarities here. So that was, I think, is it in here? Oh yeah, here we are. So if you look at the variance of the slope parameter, you have sigma squared over sxx. So with multiple linear regression, it's pretty much the same thing, except it's just generalized to the multivariate form. So you have the variance of the beta hat, which is pretty much all of your slopes, sigma squared over the multivariate generalization of this. So over here you have this, and here we have this. Okay, and so this, if somebody asks for the standard error, which I didn't print that in here. Okay, so the estimate of the variance is s squared, and this is residual sum of squares divided by n minus p minus 1. So instead of n minus 2, now you're all of the x variables, as many p as you have, you subtract this off, that many off, which makes the standard error term, whoops, you just plug in s over blah, blah, blah. Why am I I'm getting caught up here, tongue-tied. So you have s over the square root of sxx here. So you can think of, you can kind of do that, and you'd have s squared over wait, so s squared over, no, s squared times x transpose x inverse would be the standard error thing, and then you can take the root of that. Okay. Oh, so this actually burned through a lot faster than I anticipated. Well, I guess there's no harm in finishing early today. Yeah. So that's all I just wanted to cover that. You can go through all of the derivations in the book in chapter 5 for the least squares estimates. I don't know if this stuff excites you or not. Doesn't really do it for me, but it's there, okay? And so all of this stuff is valid and true. I don't know in 101B if you cover, or not 100B if you cover the multivariate form of these derivations. Probably not, but you basically, it works for linear regression, and with the multivariate form, it's just kind of this multivariate generalization of everything in matrix form, which just complicates everything and makes your head hurt, but the same principles and everything apply, and you just end up getting the same exact results. And you just have to deal with crazy things like the Jacobian and the Hessian and all of these funny matrix things. All in all, to say, beta hat is this, okay? So this is like half of chapter 5, and then on Wednesday I was going to cover actually just fitting polynomial models and then multiple regression models and all of this. I think it's rather straightforward, not too troubling. It's just in chapter 6, when we do all of the diagnostics, that's when things start to get a little bit more hairy. But we'll go through it at a nice gentle pace and make sure we understand everything along the way. Okay, so we'll wrap up a little early today, and then we'll see you guys on Wednesday.